Welcome to Lipids Part 1. In this tutorial we'll look at fatty acids and then fats and oils, also known as triglycerides. Let's get started. Alrighty, so we have talked about fatty acids before, but let's do a brief review. So palmitic acid, here is the condensed formula for palmitic acid. So let's go ahead and write out the skeletal line structure. So we can see that it has a 16 carbon chain, right? The carboxylic acid carbon, the 14 methylene groups, and the terminal carbon. So there we go. And so this is really just a carboxylic acid, but we call them fatty acids because there's a long hydrophobic tail, right? That wants London forces. So this part of the molecule loves to be with other fats. Of course, the carboxylic acid part is polar and wants to be with water. But this long hydrocarbon tail wins. So this would not be soluble in water. This would be fat soluble. Okay. So, since we studied this before, we got kind of warmed up there a little bit. Here are 4 different fatty acids, and so fatty acids are described, right, based off of the hydrocarbon tail. So this is how we distinguish between fatty acids. So let's practice making that distinction. So one of these fatty acids is saturated, another one is unsaturated, and one of them is polyunsaturated. And for the unsaturated, we can go ahead and make a further distinction. Does it have cis or trans carbon-carbon double bonds? Alrighty, so take a moment to describe these fatty acids, and then we'll compare answers. Alrighty. So here we can see stearic acid is similar to palmitic, that it's a saturated fat because the hydrocarbon tail has the maximum number of hydrogens. And then when we look at oleic acid, which is found in olive oil, we see that there is a double bond present, and here is oleic acid, there's also a double bond present. So when we look at these 2 fatty acids, we would say they're unsaturated because we lost, right, we lost some hydrogens to form the double bonds. So now we can further distinguish between the unsaturated fatty acids. Here we would see a cis double bond, and here we would see a trans double bond, right? And so then we want to keep in mind that in Mother Nature, we only find cis double bonds, and that trans double bonds, right, are man-made. Okay, and then for this last fatty acid here, now we see that we have more than one double bond. So we would describe this as polyunsaturated. Okay, and there's linoleic acid. Alrighty, now let's arrange the fatty acids in order of decreasing melting point. So we'll start with the highest melting point, and we'll go to the lowest melting point. And so remember that the highest melting point, right, that's going to be a solid at room temperature. And so it's going to have, right, the strongest IMFs, intermolecular interactions. So if we look, oh, excuse me. Okay. So if we look at these, right, so we want to arrange from the highest melting point, which means most likely that it's a solid at room temperature, the lowest melting point, right? It melts really easy. So these are often going to be liquids at room temperature. And if you're wondering what in the world is room temperature, it depends on who you ask, about 20 degrees C. Alrighty. So remember that it's all about, at this point, each of the molecules has one carboxylic acid group. So that's not going to be the difference. So the difference is going to come from the hydrocarbon tails. So if we look at the hydrocarbon tails, we see that the saturated makes a perfectly straight chain. So we would be able to stack one fatty acid next to the other, and we would have a huge overlap of surface area for interactions. So the saturated fat, or the saturated fatty acid, would have the highest melting point. And that would be, we could also just use the letters. So that would be A. So that is going to melt higher. So now let's look around. So using that logic, we can see that the trans, the kink in the trans, is much smaller than the kinks in the cis. And so with each kink, we are going to disrupt the interaction between two fatty acids. As we have less surface area, we are going to weaken our intermolecular forces. So next would come C, the trans fat. And then quite logically, we could see that the more kinks, the less interaction we'll get between fatty acids. So next would come B, and last would be D. All right, so this was all determined from the structure of the fatty acid tail. Okay. One last thing to look at is with our unsaturated fatty acids, we have learned two systems for naming them or classifying them. And so the first one is the omega system. And it's interesting, we have two different symbols there that we could use. And remember with the omega system that we count from the end of the fatty acid tail. So if we wanted to do the omega system here, we start here and we would say, this is an omega 6. All right, so write that there, omega 6. Now there's the delta system. Okay, so with the delta system, right, so that gets the triangle for delta. Now this is similar to IUPAC nomenclature, like if we were going to name it. We count from the carboxylic acid carbon. All right, so and the interesting thing about the delta is we include all double bonds. All right, with the omega system, we just let everybody know where the first double bond appears. But with the delta, right, so now we're going to count from the carboxylic acid. So we would say that this is delta 9, 12. All right, so the location of the double bonds is a right superscript. Right, and we would show all carbon-carbon double bonds. So they're comparing and contrasting, right? So omega starts at the end of the carbon chain, and we just give the location of the first double bond. Delta, on the other hand, we start from the carboxylic acid, and then we tell everybody where all of the double bonds are. So there's a brief review of fatty acids, and now we will look more closely at fats and oils. But fatty acids are a major component of fats and oils, so it's a great place to start. Alrighty, so let's go to the next page. Alrighty, so we've been looking at, well, let's see. So let's box the glycerin backbone and circle the ester groups, and then take our knowledge of fatty acids and use it to explain how the R groups would affect the physical state of the triglycerides. And just linguistically, before we get too far, right? So fats imply that they come from animals, oils from plants, right? But then chemically, we don't really care about the origins when we think about it. We just call it a triglyceride because of this glycerin backbone. They also get called triacylglycerides, and that can get abbreviated as a TAG. So lots of synonyms. Alrighty, so let's box the glycerin backbone. And so this is our glycerin backbone, right? So it's just a triol, right? 3 alcohols all together. And then we'll circle the ester groups. So then here would be the ester groups right there. And then as we just saw from our fatty acid review, right, that saturated and trans R groups, right, tightly pack to form solids at room temperature. And that when we have the cis double bonds, cis R groups have bends, right, that weaken the interactions, and so that right, that tend to form liquids at room temperature. Okay, so there's the overall structure. So basically, it's just 3 esters, right? And the main reactions that triglycerides can occur are reduction or hydrogenation, which is the source of trans fats. Oxidation, if you've ever smelt rancid butter, right, rancidity. And then hydrolysis, which we can use for catabolism or to make soap, saponification. So we have a fat molecule here, can barely fit it, and then you can look and you should be able to classify and recognize which reaction is rich. So I'll give you a moment to do that. Alrighty, right? So in this first reaction, we notice, we have an addition of oxygen. So this is clearly an oxidation reaction, right, that leads to rancidity. When we look at the second reaction, we notice, everything was all bent here. We had a bunch of cis double bonds. And what happened, right? We lost some of our double bonds, and then we ended up with a trans double bond. So this would be our reduction. So when we talk about, right, so this would be, for an example, a hydrogenated oil, right? So we would, with all of the cis bonds here, this is probably an oil, right? It's going to be a liquid at room temperature. And so then the processed food industry does the reduction to make the hydrogenated oils. There's several reasons why they do this. One is because now if we look at this hydrogenated oil, would we expect it to be a liquid or a solid? Notice that now it is most likely a solid, right? And here we would expect it to be a liquid. So hydrogenated oils are really great for the processed food industry because we go from a liquid to a solid. And solids are much easier to keep care of because if you spill them, they don't make such a big mess. Another advantage for the processed food industry is that molds don't like to eat hydrogenated oils, and so they become rancid slower. However, these benefits to processed food are not benefits for us. My own personal rule of thumb is if it's not good enough for mold, it's not good enough for me. And what we're going to learn is in this chapter is that the fatty acids and lipids are important to our cell membranes, and our cell membranes are very important to our overall health. Our cell membranes are the gatekeepers of our cell, letting in and out nutrients and wastes. And so it's very disconcerting to think about having changes in the basic structure of the building blocks for our cell membranes. And that is why now trans fats are no longer allowed in food, and there must be labels for them because of these health concerns. And then last but not least, let's look at the hydrolysis. So here we would have some kind of lipase, and of course we would need water. And then we can look in here, and by now we're experts. We find the carbonyl carbon, and we know the water will come in and hydrolyze each of the ester bonds. And so then we can see that these hydrogens came from the water, and these hydroxyl groups came from the water. And so we have basically a simple ester hydrolysis. The only trick is that we need 3 water molecules because there are 3 ester groups. All right, okay. So we've gone through the basic structure of fats and oils and the 3 main reactions that they undergo. And so now just do a little bit of connection to our functional group reactions to help bridge what we learned in very simple organic molecules a few weeks ago, and now what we're applying to these more complicated biochemical molecules, right? So let's look at these 3 reactions: the ester, the thioester, and the amide, each reacting with water. And notice what results: carboxylic acids. And then we remember we were calling these the Z's, right? The alcohol, the thiol, or the amine. So what reaction is shown? It's the same classification, right? These are all hydrolysis. So that's what we're it's an important reaction for biochemistry. And so whenever we're looking at hydrolysis of a carboxylic acid derivative, we focus on the carbonyl carbon, and we know the water is going to come in. The hydroxyl group will go with the carbonyl, and the hydrogen with, right, what we call the Z group. And so here are the hydroxyl groups and the hydrogens. And there is our carbonyl carbon. All right? So just remembering everything we've learned about hydrolysis, and now applying it to triglycerides. So here is a molecule for us to practice on, right? So here we have a triglyceride. And so if we have 1 mole of triglyceride, how many moles of water are needed? All right? So we're definitely going to need 3 moles of water, because we have 3 esters to hydrolyze. So now let's go ahead and predict the products, right? So to predict the products, we are going to focus on our carbonyl carbons, recognizing where to hydrolyze. Now there's not a lot of room here, so I'm going to show, right, there's the glycerin backbone. We'll just show that right here. Okay, and we know, whoops, right, and so we know then that the hydrogen from the water comes in, all right, and so then this will be the glycerol, right, which also could be called glycerin, So 2 names for the same structure. There we go. Now comes the trickier part. Right, so now we need to draw out each of the fatty acids. Alrighty. So this first fatty acid, I'm not sure if skeletal line will work. I don't know if we have enough room. And we don't know if they're cis or trans. So let's just go this way. Right, so we have our terminal carbon. And then we have 4 methylene groups. And then we have a double bond. And then another methylene, and another double bond, and then we have a bunch of methylenes, and then it just fits. We have our carboxylic acid. All right, so there's our first fatty acid, and then we would have the second fatty acid. This one looks a little simpler to draw. Now we have 5 methylenes. And then comes our double bond, and then we have another 7. Well, that should have been a 7. And then we have our carboxylic acid group. And then last but not least, we have a nice little saturated hydrocarbon tail with our carboxylic acid. Okay, so we have 4 products, right? So these are all of our fatty acids. And notice in this example we had a saturated, a unsaturated, and polyunsaturated, all within the same triglyceride. So, all right. So there's the main skills that we need for fatty acids and triglycerides is making sure that we can hydrolyze them and classify, distinguish between saturated, unsaturated, and polyunsaturated. So please take some time now to work homework problems to reinforce your understanding.